Thanks for everyone for joining us. We have one final presentation for you. This one is an hour long because it's a tutorial from Jeremy Spewock of UNH InterOperability Lab and Doug Ledford, the chair of the Open Fabrics Alliance and a member of Redhat. The two topics covered are how to do manual RDMA testing using the FSDP cluster and how to set up RDMA CI using the FSDP cluster. Jeremy is the lead developer working at the University of New Hampshire InterOperability Lab as part of the open source team. Doug, the chair of the OFA, was a principal software engineer at Redhat. He studied computer science at Missouri State University way back when he was introduced to Linux when it only ran from floppy disks. Doug is the former upstream maintainer of the Linux RDMA stack and the RDMA core user space project, as well as a Red Hat subject matter expert for MD software, RAID stack, and the RDMA stack. But now he's joined the dark side. He's into the management side of Red Hat operations. Doug, were you going to present, or is Jeremy going to present?
Jeremy's to start, and then I was to go after. Is Jeremy here?
He was a moment ago.
Hi, can you hear me okay?
Yeah, there you are.
Perfect. Awesome. So yeah, I will share my screen here. Everybody can see that share screen okay?
We cannot see your slides.
Right, but it's right here.
There you are.
Perfect. Awesome. So thank you so much. As mentioned, my name is Jeremy Spewock. I'm a lead developer at the University of New Hampshire InterOperability Lab, and today I'm going to give you a brief little run through of how you can do RDMA testing of various types of software using the FSDP cluster. So as a brief little overview, we're going to talk about, first I'll go through an introduction to the cluster itself. I'll sort of run you through both hardware-wise, the nodes we're looking at, as well as the software and the fabrics that we have backing there. I'll give you a tour of Beaker. Beaker is just an open source automation lab, or a automated lab managing tool, excuse me, and that we use at the FSDP cluster to manage our nodes. So I'll explain to you sort of what that is, why we chose to use that, and generally how it works. I'm going to give you a little bit of introduction to Redis as well, because Redis is what I'm going to use for the demo shortly, following right after that. Because there's something where RDMA support was proposed, and we can do a little showcase of testing on that front. So I'll give you an explanation of what Redis is that asks for RDMA support, and then I'll run through exactly how to do that. So opening up with a little bit of introduction to the cluster, starting with the hardware side of things, the main hardware that we have in the cluster are our 10 bare metal nodes, which are used more for testing environments, and then Builder 00. So starting off with the nodes, as I mentioned, the nodes are sort of your actual physical testing environments. They're in general much more transient. They're just meant for temporary nodes that you can provision, and then they have the actual hardware that you can use to hardware that supports RDMA fabrics and the networking to communicate with other nodes within the cluster. So nodes in general are where you will provision with a selected operating system, and then you will go into there and run your actual testing on the hardware. Whereas Builder 00 is our build server, and that's much more of sort of a static environment where you can actually build your artifacts, you can build your binaries, and the Builder 00 has persistent home directories for each user, in contrast to the nodes, which are re-provisioned every single time you want to run testing. So sort of, again, very transient temporary environments, but Builder 00 has an area for you to build things, and they can live there persistently. And then it also has support for hosting those binaries in a public HTML directory that the nodes can then interact with and grab those binaries. So a lot of times you'll see a workflow where you'll start out in Builder, create what you need for your testing, host it there, and then you can provision your nodes and grab from an HTTP server any of the binaries that you would need to actually run testing. And then on the software side of things, the four main fabrics that we support are iWarp, InfiniBand, Rocky, and OmniPath fabrics. On the right-hand side of your screen there, you can see sort of the breakdown of our subnetting and how we separate out those fabrics throughout the nodes. But in general, the the fact that we have these 4 different fabrics is one of the highlights of the FSDP cluster. It allows for much more diverse testing and much more full testing. Of course, when you're testing software that you want to put into you're testing RDMA support of mainstream software, you want to be able to test across multiple different fabrics to ensure that you don't have something that's, for example, if you've always been testing with InfiniBand, you don't want to have any little pieces that are only supported by InfiniBand that might not quite work the same on Rocky or OmniPath. So one of the huge highlights of the cluster is that diversity that it provides and the availability of these different types of hardware, so that not only can you test different fabrics like the 4 I have listed here, but we also break things down by specific hardware that supports the fabric. So you could even test the differences, for example, between MLX4 Rocky fabrics versus MLX5 Rocky fabrics in case there's any hardware differences as well. So in general, the cluster supports a lot of different hardware, a lot of different software, and it allows you to get a more full, diverse testing suite to ensure that your tool is working as you would expect. And then stepping into sort of how that testing is done, as I sort of mentioned before, Beaker is an open source tool that we use for our managing our automated lab. What's super useful about Beaker is it allows us to store a library of different OSs that we could use to dynamically install on the hosts, depending on your desired operating system for your testing suite. So that's sort of where you get not only diversity in hardware and software, or hardware and fabrics, but you also get the operating system differences as well, where you can test how things sort of behave on different Linux distributions. So that's super useful again for the diversity. It maintains all of the hardware on the nodes. We get a nice inventory of the nodes that we have available, what hardware they have and what they support, which makes it very easy for both the user and us as maintainers. And then we also are able to store individual tasks on Beaker, which is super useful for repeatability, because then you can write a task once and you can schedule jobs that run on various operating systems. You can choose specific fabrics that you want to run the tasks on, and you can reuse the same tasks for multiple different fabrics in testing. So that's one of the big reasons we use it, is that repeatability. Another huge reason that we use it is because it allows us to sort of, when we manage these nodes, we can also group them and pool them by what fabrics they support. So, and also what we do is not just this fabric specifically, but we could create pools, sort of as I mentioned, for testing on MLX5 Rocky, for example, versus MLX4. And so we break our pools down a little bit more granular than that by hardware as well. But what's super useful is Beaker uses a simple XML format for writing their jobs. And you could sort of write that format one time. And then because we have these pools of hosts that are assigned to different fabrics, you could very easily change in your job. I want this job to run on this operating system and 2 hosts that have this fabric, for example, and you can run the same job again and just tweak the fabric that you're pulling hosts from, and Beaker sort of dynamically looks at what hosts are available in that pool and also grabs you the best ones that would fit your needs right there. So super useful for that end, for us, for both the user scheduling nodes on different fabrics and also us sort of keeping track of things. But another huge plus, a little bit more on the back end, is the Beaker snippets. Beaker snippets essentially allow us to create kickstart files dynamically based on, you could do it based on the system, the lab, or the operating system. And what we use it mostly for is the operating system, to allow us to create different configurations for installing hosts based on what operating system you choose to have on the host. What that does is, again, it just makes it super repeatable. It makes it so your tests are very consistent. You get the same environment every time because you install the same packages, you're going through the same setup procedures, and it's super useful for just making consistent environments. So you can be confident that your tests are working as expected. And sort of stepping into the different testing methods on Beaker, I sort of touched on a couple pieces of them, but what I'm going to focus on today is more the manual process. This is essentially when you go through Beaker, you look at that list of nodes, you provision a node, and Beaker reserves that and gives you access via SSH. It has support for using either your SSH keys, or you can set a root password in Beaker, because Beaker gives you root access to these hosts. And sort of the highlight of doing it the manual way is you're able to get this temporary testing environment. And because you have root access, you can make any little tweaks or configuration changes that you might need to make on the fly run your testing, see the results, and once again, make that testing or make those changes anywhere you need to. And then I also alluded to before that the manual way benefits a lot from the HTTP endpoints on Beaker or Builder, excuse me, because you're able to grab those binaries that you built off of Builder, run testing with them, and do whatever tweaks you need to do, as opposed to automated process, which I talked about a little bit before, where you can write XML jobs using Beaker's format, and then you can create different RPMs to run your testing automatically for you, and then just sort of schedule those tests under the hosts dynamically based on their pool. So in general, I think of the manual process as a much more flexible way to do things. You're able to install what you configure the host as needed, grab those binaries that you need to run testing, and then sort of as you run that testing, you can make your modifications and tweaks without having to re-provision the host, whereas the automated process is much more repeatable and consistent because you get the same environment and the same testing, no matter the operating system or the fabric that you're looking for. However, those hosts get freed right after testing is finished. So that automated process, you kind of have to re-provision if you want to make tweaks. And those are sort of the two main processes, but again, I'll be focusing a little bit more on the manual process for the demo in a little bit. And moving on from Beaker, we're going to step into, again, just a little bit of background on Redis, just so we understand why this demo is valuable. Redis, if you don't know, it's a high-speed in-memory database. It's what's known as a data structure server, meaning that Redis sort of is a database that supports specific data structures that they provide. And then they allow you to interact with those data structures and call commands on the different objects through over TCP with the client server model. Of course, it's in memory, but it's also non-volatile, because what would use would that data be if we just lost it? So, of course, Redis does also save to disk every now and then. So you sort of get the speed of the in-memory operations by it staying in memory to do the operations, but that saves to disk every now and then to keep your persistent data. And right off the bat, we can kind of see how RDMA would fit right in with something like this, because they're using sort of that client server model and remotely interacting with the objects through TCP that are in memory with the database. But it wasn't something that was originally shipped with Redis. And as for RDMA and Redis, a little while ago, there was a ticket opened. Well, actually, it's been a decent while now. In July of 2021, someone opened a ticket asking for support of RDMA and Redis. And generally, you would think with tickets that are open for that long without really a resolution, that it kind of got dropped, or wasn't super popular. But this ticket actually had a lot of traction with the Redis maintainers. There was a lot of people looking at it, and in general, people supported the idea of RDMA support built into Redis. But it's, again, been open for so long and unresolved because of two main blocking points. And those blocking points are a general lack of knowledge about RDMA from the maintainers, and then also a call for testing of this branch on Redis to ensure that, of course, if you can have built-in support, that it is as functional and maintained as they would hope. So currently, it's only been tested by the author of the commit himself, who tested it on soft Rocky Fabric. And he also tested it with a Rocky Fabric using a ConnectX-5 card. But it's understandable why this doesn't make the maintainers 100% comfortable with merging it as built-in support yet, as it's not really a full testing suite. It's more so just on a single fabric on a single type of hardware. So there was sort of a call to ensure that this is working on multiple fabrics, and it would fit the needs of Redis across different types of hardware. And there were a couple ideas proposed to do this, one of which was AWS, which at the time only had a partial implementation of their own proprietary RDMA capability that was available for users to do testing. Which again, didn't really show from a consumer side a full testing suite that would make the maintainers comfortable. And also Azure had some RDMA support, but only specifically with Mellanox and InfiniBand. And once again, you can see how this is exactly where the FSDP cluster fits in, because that offers a plethora of fabrics that you can use for testing multiple different types of hardware. And even if you can't support every fabric, you can at least be confident that it works on, you can be confident on the fabrics that it works on and the hardware that it's capable with versus ones that it might have a couple more caveats and gotchas. So that sort of concludes our general overview of Redis, Beaker, the cluster in general. And I'll move directly into a bit more of our tutorial and demo. And you'll see here, the first place you're going to want to go when you're dealing with scheduling these nodes yourself is through Beaker. So once you land on Beaker, this is the landing page you'll see. As you can see, it keeps an inventory of nodes that are available for those different testing environments. You can see that I have a couple booked here already that I grabbed ahead of time. And one of the main ways when you're doing this manual process that you're going to understand which host that you want to grab is through the pools that I mentioned that Beaker offered. So you can sort of see what I was talking about here, where we group hosts based on different fabrics and different hardwares. So you can see we have a pool in general for InfiniBand, and then we have subsets of that pool for specifically MLX4, InfiniBand, and MLX5, and the list goes on. Each of these has individual nodes inside of them, so you can see the nodes that support InfiniBand fabrics. So in my case, I grabbed nodes 1 and 2 and 9 and 10. 1 and 2 primarily for the OPA fabric here, and 9 and 10 has supports multiple others such as Rocky, I believe it is iWarp, and a few others that we'll see once we log into that host. So in general with Beaker, you sort of start out by looking at the pools that are there, the fabrics that are available, and what nodes you can sort of grab in different pools. And then what you're going to want to do is, as I alluded to before, when you click the scheduler drop down, there's a reserve option in Beaker. And this sort of allows you to pick the distro that you want on the node. So in my case, I'm using Fedora 39 just to make building RPMs a little bit easier because they have their own built-in source RPMs that I can use. You could select distro trees, and then you can either let Beaker decide any system and any system specific from this lab, or of course we can grab specific nodes right here, which I had already done beforehand. And once you submit this job, Beaker will go ahead and provision the operating system of your choice on that node. It'll configure the host through the Kickstart file that it compiles through snippets, and then it will make that host available to you via SSH. So I always recommend that you grab the nodes first, just because while it's not an unreasonable amount of time that it takes for them to provision, they are bare metal hosts, so it's a non-negligible amount of time that it takes to configure them and start them up. So in general, if you book those nodes first, and then you move over to Builder here, I'll make that a little bit larger. Builder 00, as I mentioned, that's our build server with our persistent environment. So all members get their own users on here with their home directories that they can use to build whatever packages they would like to. And from here, another thing that's available on Builder, it's Podman to create sort of different, of course, because in my case, I decided to grab a source RPM for Fedora 39 since they already have Redis available that way, and then sort of modify the RPM and repackage it myself. I'm able to build this container here off of a Docker file. Super simple Docker file. All I do is I grab Fedora 39, install a couple packages for building RPMs, and then I built this container image right here. We do also have some container images hosted on a registry that's managed by the CKI project. And there's some information about that on our GitHub page in our documentation. But in general, I found it easier to just build myself a very light container for this. Jump into that container very quickly. Privileged. We'll find out how to spell privileged, I believe. And then we do going to mount our current directory into the container, add this in the MNT directory, run this tag. Of course, I spelled it wrong. not one of my strong suits exactly is spelling. We'll grab. Like, tell me where it is. Okay. Well, instead of using privilege, we can also just use instead. It's only really for SE Linux, so I can just do :Z here as well, which will give me access to those files. Just because when you're running rootless podman, there's permission different issues when you're accessing files that are in your home directory with SE Linux. But now if I'm going to first run this script, and then I'll sort of explain what I'm doing in the script as it goes, because it's going to take a minute to have that finish. And I'll specify that I want to build the server first. And I also need to specify side specifically at RPM. All right, always a couple little snags when you're doing it live. So if we open a new terminal here and we have to back into builder 00, see back to this demo. The reason I have this small script to sort of make my changes, all it's doing is it's going to install that source RPM, which builds you this RPM build directory in your home directory. And then there's a couple changes I need to make to the source RPM to be able to compile with the RDMA support. And these are outlined in the pull request on Redis, but essentially I'm just cloning the main Redis branch. I'm grabbing the pull request here as a patch, applying that patch, and then I need to make some modifications to the spec file, which add the make flags that are required to build the RDMA. And then in my case, because it's not quite offered as built-in support on this patch, and it's instead just building RDMA support as a separate module, I also need to mount that module somewhere where I can use it. So I add that to the spec file, and then I add it to tracked files right here for the server. And then Redis changed their licensing at some point. So this version of Redis spec file is expecting a license file that's not there anymore. And if we jump back here, this should be finishing up. Perfect. And now you'll see that in my home directory in RPM build, I've got some new RPMs to run with. Just labeled this. And I can move this into that mounted directory I had that sort of mounts it to the outside world. And I'll call it demo server.rpm, move it right there. And then here, back on Builder, now that I have this RPM available, I can copy the RPM back into the public HTML directory in my home directory on Builder. And what this does is it's going to serve at that HTTP endpoint of 00 OFA, my user, right through there. You'll see that now we have this demo server RPM right there. That I'll be able to access through the same HTTP endpoint on the nodes to grab that demo RPM. So if we jump back here, one other thing that you have to be aware of is, once again, SE Linux, bane of a lot of moving these sort of things around between containers and different environments. If we look at the public HTML directory and its contents here, you'll notice that the type of what I just moved over this demo server right here. Oh, sometimes if you create a file in your home directory and you move it into your public HTML directory, this SE Linux type will not update properly, but it looks like it did in this case. So we have that HTTP user content right there. And if I move over to SSHing onto root node 1, sorry, this is just because when you reprovision, it changes its keys and everything because it reprovisions and installs the operating system. You can see I'm on node 1, and we have this interface here that's pre-configured for you for the OPA fabric. If I SSH and it's a node root node 2. We get the same thing with that fabric right there. We can do a nice --k, this address right here. Oops, did not grab the address properly. Back here, we'll curl builder at my endpoint right there and do demo server.rpm. Oops, I forgot to give it an output. We'll call that server.rpm. We get that right there. So now we can just do a nice yum install server RPM. And what's very nice about just sort of taking the source, modifying it slightly, repackaging it as an RPM again, and then hosting it on Builder. It's super easy for me to just install as you would on any old operating system on Fedora normally, your general Redis. That's going to install right there. And then here, I'll once again do /k of client RPM, same place right here. I had just for the sake of time, client RPM already made. Once again, if we install the client right here, so I'll make that bigger again as well. The Redis client's going to be installed. And here, something I changed in the spec file was mounting the module that we need to etc Redis. So it's right there with the Redis configuration. If we grab these commands that were recommended by the author of the commit, paste this here. And we grab this as well. Something else that he had highlighted there was that what we're going to need, we bind this to the address of our OPA fabric. Grab just a couple more flags here. Sorry for all the jumping around. That's all right there. And then once again, when we load the module, as I mentioned, we mounted it in etc Redis. And that binds, and you can see that it's ready to accept connections over RDMA. We can move over to node 2 over here where we have the same thing installed. And we're going to grab the client commands also from the pull request created by the author. I'll turn down the number of packets being sent just for the sake of demonstration, because the full time is a little bit long. We're going to want to use that same IP address that we bound to here for the OPA fabric. And with any luck, when we run the client over here, our benchmark, you can see that we're running that same RDMA benchmark, but we are running the client side provided sort of by this user. So doing this, we can fully test exactly running Redis, both the server and client, through the RDMA supported module, simply by grabbing those a couple RPMs off of Builder, or well, first building the RPMs on Builder, grabbing them on the nodes, installing them quickly, and then just running the client and the server. And that's all it takes to be able to test on OPA through the FSDP cluster. And yeah, of course, you could do the same thing, grabbing those RPMs on various different operating systems. I chose Fedora 39. You can grab multiple nodes like we had node 9 and 10 and run them on different fabrics. And you're able to test the diversity and the differences between all the different hardware and fabrics. And that is all I have for my end of the presentation. Thank you very much.
All right, thanks, Jeremy. So with that, I'll pick up now. Let me go ahead and share my presentation. All right, so this kind of picks up a little bit of the same thing. Although in this case, I let Jeremy do his work of getting Redis up and running on the cluster and able to actually pass tests and everything else. And then I went in and set up a talk about how to actually hook that into the CI that we run inside of the FSDP cluster. So in a very, very loose sense, the steps required to hook everything into and this does hook into the KCI infrastructure that Redhat built over the years. The first thing you have to do is you have to create your tests. After that, you have to add your test to the KPET-DB, which is part of CentOS Stream. Then you have to add your pipeline to the OFA pipelines in KCI. And then you just sit back and let it do its thing. It's really what it boils down to in a nutshell. I'm going to try and be quick with this. So let's go. So first of all, creating your test. Well, the nice part about this is Jeremy's already covered a lot of what needs to be done in terms of creating your test. So Jeremy's already shown you how you can get the thing built, how you can run the Redis benchmark and everything else. He's also demonstrated how you can use Builder 00 as an artifact repository. You can create your own little build environment on Builder 00, et cetera, et cetera. So the question is, how do you tie that in into the test infrastructure? And the general basic thing is that you have to add it to the FSDP test repository on GitHub. So I've given you the links for cloning the FSDP test repository here. And so you just need to create your own directory inside the test repository. Fortunately, the test repository only stores very small static text files, basically, usually shell scripts that tell things how to run or make files, things like that. So a single file or a single test does not take up much space here at all. The whole purpose of the files in the test repo is simply to script the other things that have to be done. Like for instance, whenever you run these machines in the FSDP cluster in an automated fashion, they always get the restraint test and harness installed. And so you can just use that as you're working with your tests. You have all of the restraint capabilities at your fingertips. So you would basically just add your own unique directory for the tests, and then it's whatever scripting you need in order to get the stuff pulled down. The one caveat here is that we do have to have some separation for the tests based upon which ones you want to run on which pool machines. And this is because there's a template file, an XLS file, that's used to specify pools for machines and other factors for the test. And we don't have a good way of having a single test directory that can be run on multiple different fabrics. So what you can end up doing is you can create a common directory with a generic copy of your test files, and then a separate directory that's specific for the XLS that you need for a given machine in the infrastructure. And by the way, there's also been additional demos and videos about this in the past, and I left those over here on the left-hand side, so if people want to look that up, they can. So like I said, the first thing you have to do is you just create your test. There is a demo in the FSDP test repo that gives a pretty good idea of how you can go about doing that. And so I'm going to talk a little bit here about how you can just simply copy the majority of the demo tests into your own directory to get a start. So in the demo tests, there's a file called runtest.shell. This is actually the thing that's going to get run by Beaker whenever it starts to run your tests. And in that runtest.shell, there's a function client, a function server, and then not as part of a function, just so Bash will go ahead and run it immediately. We have this section called start test. And all I really want to point out here is that on the client, you'll see that we do a sync block and a sync set before we actually run the client tests. And it calls into a separate file for the client test. And the same thing here for the server. And then before it ever does the client or the server, it calls this common, right? And so the easy way to set this up is just to copy the run test over. Rename the tier1.shell to whatever your test needs to be, whether it's redis.shell or something else. You probably don't want to use that same name. The tier 1 name is what we use for our basic kernel testing that's just intended to go ahead and verify that the kernel works on specific hardware. But what you want to do is you want to tag this tier 1 or whatever name you put on your shell, tag this common function as the section of your test where you actually download, install, build, or whatever you need to do to your software to get it installed on the machine. And I'm going to get into that more a little bit later. But essentially, if you're wanting to test user space software using this infrastructure, then part of the test is getting that software installed. Because otherwise, the only thing you're going to get is you're going to get the software that the distribution already has. So if you run it on Fedora 39, you're going to get Fedora 39's Redis. You would have to do something like Jeremy did, where you have the Redis RPMs available on Builder, and in this common section, download and install those Redis RPMs in order to have that happen. However, that's probably not what you want to do for something where you're doing CI, because you're just going to test the same RPMs over and over again. You're going to want to do something different. And in this case, probably what you're going to want to do is you would have a branch that you're watching in an upstream Git repo, and you'd want to pull that branch down and build that branch. And so your common function may be a little bit longer than the one here, just because of the fact that it will likely need to do something like that. So like I said, you can start by just copying the majority of these files across, and you don't even have to modify most of them. You'd want to modify the run test and rename tier 1 to whatever your test is going to be. And then you will need to take the tier 1 we have, probably strip out most of the test part, but you could leave some of the synchronization and logging and copying of data parts in. And then turn around and modify the common client and server functions to do what you need to do for your tests. And so I took a quick look at the tier 1 just to demonstrate what I'm talking about. And so, you know, I started up here with the common tests. And this is not the entire common test by any stretch of the imagination. I cut that off. I was just showing you the fact that the function is there. But it is the proper place to put your build install stuff. So if you want to do the wcheck or wget like Jeremy did, you can do that. But you can also do the builds and everything else right here. But the important part here is the common stuff is run before the client and server, and the client and server do a sync up before they actually run the client and server stuff, which makes sure everybody has finished their common tasks before the actual tests start. And so then that gets into the server tests and the client tests. And so there's some various error checking boilerplate inside of these functions. You can leave it, you can rip it out, you can do whatever you want. Obviously, it's there for a reason. We've found over the years that sometimes machines don't come up with the right IP addresses. Maybe the DHCP server's down or something like that. And avoiding getting failed test reports because the DHCP server is down and your machine doesn't have your IPv4 address just saves you the time of hunting down why a command or why a particular run failed. So I would recommend leaving the boilerplate in and then making it so that on the event that, you know, something fails for a boilerplate reason versus an actual test failure, it doesn't get flagged as a false test result. Or actually, you want it flagged as a false failure, not as a true failure. But in the client and server, this would be where you'd be running the commands Jeremy just demonstrated. One of the things that the restraint harness does is it has an expect capability in it, so that when you run these commands, you can tell it, you know, expect this output or expect that output. And based upon the results of the output, you can then turn around and trigger whether or not this is a successful test run or a failed test run. So that's actually the biggest part of writing the tests. You've got free form to go in and do that shell script however you want. You know, you're going to run the run test.shell script. In order to keep that from having to be modified a whole bunch of times all over the place, you want it to call your own custom script so that the run test stays pretty static. It makes it easier to copy things around and do more tests in the future. And then your own test file is a free-form scriptable shell script so that you can do pretty much anything you want, anything you want. So, including things you can run more than one series of synchronized tests if you want. So, for example, you know, it had a sync section before it ran the client. Well, inside the client, you could actually call your own sync and run different stages of the tests at different times with synchronization between the client and server. So after you get your tests written, you have to add your test to the KPET-DB. And so I really don't know what KPET-DB stands for. It's kernel something database. It's one of those acronyms that's lost on me, sorry. So this is the Git repo for the KPET-DB. It's on GitLab. It's part of the CentOS stream, and it's the list of kernel tests we have against the kernel. So Redhat for a couple decades has been doing QA of our kernels. Recently, we've started open sourcing all of our internal testing. That doesn't mean that it's all been open source at this point by any stretch of the imagination. We actually have to do our normal day job during the day too. So we have been open sourcing it and moving stuff out into it, and that's what KPET-DB is about. So KPET-DB allows us a place to specify parameters around tests, where the tests can be found, what the tests require, and everything else. So examples. One of the things in the KPET-DB is a directory called host types. And right now, existing in the host types directory are 4 different host types that begin with the OFA prefix. So Jeremy talked about being able to pull up a value of a pool in order to get a specific device. That's actually extremely valuable and useful, but we haven't needed to do it because we haven't been running a whole bunch of CI. So the the host type files for those other pools do not necessarily exist. We've got host types for IB, IWARP, OPA, and Rocky, and those are all the standard fabrics. But if you want to get more specific, such as Rocky MLX, we would actually have to go ahead and add the new host type files. But that's okay. Looking over here on the right-hand column, those host type files are just dirt simple, man. A pool op equals value equals, and then the pool you want. And if you're logged into the FSDP cluster and you pull up the pools, just like Jeremy did during his presentation, you can see all of the available pools and you can use those in your host types. If there's any pools we don't have that you find you would like that would be useful, that's certainly something we can do with the FSDP's Beaker administration. We can add the different pools. But if you do add a new pool type, in order to be able to specify specific hosts inside of the cluster, then the pool type has to be tied in inside of the KPET-DB's index.yaml file. And so that's what this slide is all about. So right now inside of the index.yaml, we have the OFA Rocky entries that you see here. They're very simple, but we don't have a specific domain on them. We only have the OFA host requires. Oh, I'm sorry, I misdid that. The OFA domain is supposed to be up on the domain line. My copy and paste did not work properly on that. So anyway, domain should be OFA, and then host requires should be the file here. To add it for the Rocky, it's the same basic thing. You just add a new host type, OFA Rocky MLX1, and then domain OFA, and then the host requires, and you put the OFA Rocky MLX file. And this will cause the CKI infrastructure to do the right thing. But that'll create the OFA Rocky MLX hosts. And then after that, you have to similarly add these lines also in the index.yaml, but now under the recipe sets, you have to go down and create a new recipe set for a multi-host recipe set for OFA Rocky MLX. And it would be the 2 hosts that we just linked in using the host restrictions. So that creates a chain of dependencies that gets us 2 hosts for a recipe, both utilizing a specific pool on the OFA cluster. All right. Then after that, you need to go into the cases directory that's part of the KPET-DB, and you need to add a directory for your case, for your test case. And as far as this goes, we request that everybody keep everything under the top level directory cases/OFA. So we don't really want to have OFA cases, test cases spread around other sections of the test case directory because they only run on the OFA infrastructure. But in this particular case, if you were wanting to do a Rocky test on Redis, then you would need to do a OFA Redis Rocky. And then in the OFA Redis Rocky directory, create an index.yaml. VI is the proper way to do that, the only proper way to do that. Okay, so one thing I want to point out here, though, is this is where we run into the limitation of machine selection for Beaker job scheduling. If you wanted to run the test on Rocky and InfiniBand and OPA and iWarp, then in the end, you're going to have to specify 4 separate test cases, because in order to ensure that it runs on Rocky, we have to put it on a Rocky specific host. And in order to know it runs on IB, we have to do an IB specific host. If you tried to put all of those requirements on a single host, aka run all of the tests on a single test specification, the Beaker instance ends up saying, okay, we can't satisfy all these requirements with one host, and it ends up just skipping the test entirely. So it does not get run. So in that case, if you want to do that, what you have to do is you create, like, for instance, Redis Rocky. And you know where, the location is the top level directory inside the FSDP tests. I just assumed we would make a Redis directory. Target sources are kernel sources that, if they are changed, could cause this to need to be rerun. For user space packages, this doesn't do anything. This is mainly whenever if you're doing kernel testing and it sees updated files in this directory, it can trigger this test. Max duration seconds. Tests do sometimes hang, and especially for odd reasons you may not expect. The Beaker scheduler is not the smartest multi-host scheduler ever created. It was originally written just to schedule on a single host at a time, never to run multi-host. And so if you start up, let's say, an OPA job that needs 2 hosts and a Rocky job that needs 2 hosts, and one of the hosts happens to have, or a host in the cluster has both OPA and Rocky, and the Rocky host, one of the 2 Rocky hosts, gets picked as one of the OPA hosts. Now the OPA host has been blocked, or at least one of them has. And if you start the OPA job and there's only one available OPA host, it'll grab the one available, and then it'll wait seemingly forever for the Rocky job on the other OPA host to finish and try to grab that host. And there are actually situations in which multi-host jobs can get themselves into a deadlock situation where one job got one of the 2 hosts, the other job got one of the 2 hosts, but they're both fighting over the same 2 hosts, and then they never finish. There's other reasons why you might want to have this cancel out at some period of time, and an example for that would, again, be DHCP server is down, because if something happens to the DHCP server, then all of the fabric inside of the cluster just goes down, and we have to restart the DHCP server. If you need a specific driver, you can load it here, but really we have the ability to specify drivers as pools, and that's actually more reliable than this is right here. So if your index.yaml file is a superset of tests, then you can put stuff under cases. So, like, for instance, you could have additional Rocky cases under here. But this is where you can get in the problem where if you have a Rocky and an IB and an iWarp under the cases here, you can create an impossible to satisfy situation and the test never runs. And then finally, you can specify sets, and you can specify as part of OFA Rocky or whatever. One caveat there, if you're going to specify as part of a set, then you need to go back to the index.yaml in this database or in the KPET-DB and add it to the list of known sets, because they have a list of sets. So it's not just, you know, free form, put whatever sets you want in there. You have to define the set before you can use it here in the sets area. So if we wanted to do Rocky and IB, we would do this twice, once for Redis Rocky and once for Redis IB. And then that would get us our specified tests. Now, once you've got that done, you still have to go back into the main index.yaml, or the main OFA index.yaml, and go ahead and link this into the cases under the OFA. So this would list this as an OFA test case. This, by the way, is not technically required. This is just a way for us to keep track of all of the various cases that have been defined. And finally, you would need to add the test to the OFA pipeline. So this is yet another GitLab repo, this time the CKI project pipeline data. And there is an OFA.yaml file. So we have our own specific pipeline file here. I'll let you guys go in and take a look at that file anytime you want. It's pretty self-explanatory. Everything in the defaults section carries through to all of the tests, which allows us to write the tests in very, very few lines. So I could add the Redis Rocky here in just these few lines. So this first little bit here is just the name of the test, and it doesn't really matter here. This is just what we're going to call it in the OFA YAML. This will be what the pipeline's named. The get URL is the upstream kernel URL you're going to use, because keeping in mind that these tests for user space packages in particular, like for instance, say the RDMA core, may very well rely upon code that's in for next of the upstream kernel in order to run. And as a matter of fact, I would hope it is, because when you're putting new code into RDMA core, you want it to match that for next, especially, you know, you want the for next of each one of those to match up. So this URL is the kernel that we're going to actually use. And this is the branch we're going to use whenever we build that kernel, because the first thing that, well, I'll get into this here in a minute. Then we have a test regex. So the name of the Redis file, let me go back here. You see the name was Redis Rocky, and, you know, pretty caps, all that kind of stuff, right? When you get to the OFA pipeline, this test regex will pull out the tests from the OFA test set based upon what you put in here. So this regex will pull out the Redis Rocky test, and that's it. That's all it's going to pull out. And then you have a watch URL, which in this case would be the Redis GitHub, and then a branch. So whichever branch name the patch is on is what we would want to watch here. And so when something happens on that branch, a bunch of stuff gets triggered. And so let's walk through that real quick. If you were to put that in, then the CKI pipelines will watch the watch URL and watch branch of your upstream repo. When new commits are added, it triggers a run. When it does that, it's going to do a number of different things, but it's going to build a kernel as requested in the get URL and the branches part of it. If those artifacts are already built, great, it'll reuse them, so it doesn't just build willy-nilly. Once the artifacts are ready, it then starts looking through your test specification from the kpetdb to get all the necessary information about the test. It pulls out all of the XML, all of the XSL or XLS, and does the work necessary to build the Beaker files, the XML files suitable for automated job submission. It then tries to submit that to the OFA cluster Beaker controller. Once the job's been submitted there, Beaker will attempt to satisfy the pool requirements and check out machines, and then it'll provision those machines, it'll install the base OS, and then it will run your specific tests on those machines. And at that point, it's all down to just running the tests, logging the results, and sending the results back to you. Of course, if there's any errors in your test specification, your kpetdb entry, or the OFA pipeline entry, any or all of that could fail. And so that's stuff that might need to be debugged once you get the stuff originally put in. But that is the process in a nutshell. And that would get your project hooked into the CI. And then from that point on, anytime you put new branch or new commits on that branch you're watching for the upstream URL, it's going to run all these tests. And then based upon how you specify things, it's going to email you the results or email it to a mailing list or whatever the case may be, so that you know how things done. That way you get your automatic testing and things are just the way people want them. Yeah. Okay, that's me. Except for I didn't fill out the last slide. So that is that in a nutshell.
Cool. Thank you, Doug. Could you clarify who's able to access the FSDP cluster, please?
Sure. The FSDP cluster is open to all OFA members. In addition, we actually make it available also to individual open source upstream developers. So maybe you're a developer working on Redis, but you don't work for a company that's a member of the OFA. We'll happily make you an individual account.
And that leads to my next question: is how do you get an account?
How do you get an account? That's a better question. Let's see. Let me reshare. All right, this video link here is the one that was to a webinar a couple of years ago, actually, with a deep dive, but it absolutely goes into how to get your account. In a nutshell, you can go to the GitHub FSDP docs, and there is an application there for an account where you can fill out that you're an individual, and then you just email that to the FSDP. I don't know if FSDP, it's in the doc, the FSDP docs instructions for how to set up an account, the email address you send it to. Cool. I don't think it goes to the working group, but we've got an alias specifically for account creation. So all you got to do is send your application to that. But the application itself is in the FSDP docs repo on GitHub. If you'd like, I can pull that up.
Hey, you might as well. Got a couple minutes. And as a reminder, if you want to see the links that are in this presentation or other presentations, the presentations themselves and the slides will be available.
Okay, you should be looking at the FSDP docs repo.
We are.
And there is an account request docx or an account request PDF, either one. And that includes all the instructions you need to get the account, as well as the form to fill out.
Cool.
And that is Open Fabrics FSDP docs.
Great. Thank you to both.
Yep.
Thank you, Jeremy. Thank you, Doug. Okay, are there any questions for Doug before we wrap up for the day?